Assalamu alaikum students. This video is related to find out the focal length of a convex lens by different methods and also contains some questions in which we find out the image formed by plane mirror, image formed by convex lens and concave lens. Okay, so we'll start with the topic of finding out the focal length of a convex lens. The quick method is to obtain the image of a distant object. Okay, so how do we get the image of a distant object? We take the lens, we put it in a holder, lens holders are available, and we take it near to the window and we can get the image of a distant object uh, on a screen. The screen has to be placed on the other side. Okay, so this distant object, the rays are parallel, so real and inverted image will be formed on the screen. So since these are the distant object and we know that the rays which are coming from the distant object are parallel to each other, and after passing through the lens they become parallel to they pass through f. It means the screen is placed at f, so that will give us the focal length. So the converging lens, this one, parallel rays, they get focus here. It means the screen is placed here at this position. The rays are coming from the distant object, so they are parallel and they will all focus at this point. If the screen is here, the image of that object from which the rays are coming will be formed on the screen. This will be inverted and diminished image. The second method is using an illuminated object and a plane mirror. The first method was actually that is estimation only. Okay, that won't give you exact, that is just approximate focal length. The first method, that is obtaining image of a distant object, gives you approximate focal length, and this we do usually so that we can carry out any experiment by knowing the value of approximate focal length of the focal length, so that we can keep the object beyond the focal point. Because if the object is placed between f and optical center, means very close, the image will not be formed on the screen, and that will be virtual image, and that is the purpose of magnifying glass. So if you want to obtain a real image, it means your object has to be uh, beyond focal point at least. Okay, so the other method is what, using an illuminated object and a plane mirror. So here, this is cardboard where in which we have cut a triangle. So this is a hole. So now this is the front view of that cardboard, and now this cardboard is placed here. This is the side view, and behind this is a lamp. Okay, so this has become your illuminated object. This assembly of cardboard sheet with a triangular hole. You can have any shape, hole of any shape, but using triangular hole is easy because the inverted image you can easily identify because the triangle will come upside, it will appear upside down, means the apex of the triangle will come uh, at the bottom, and this will, the flat size base will be appearing up. Okay, so uh, that is why to make the illuminated object we draw usually triangle. Okay, square has a symmetry, so you can't identify whether it's the image or the object. In the same way, circle, you can cut the circle also, and if you have a circle you can use a set square, cross wire in the circle. Okay, so here this is a lamp and this is the cardboard sheet. So this has become point illuminated object, point source. Okay, so the rays, they are going this way. If this is placed at the focal point, you know the reverse of this, the parallel rays coming from the distant object, they become parallel. In the same way, the rays which come from the focal point, they will, after passing through the lens, become parallel. Okay, so this is the opposite path which was shown in this. The rays, parallel rays focus here. In the same way, rays going this way, they will become parallel. So now here we have placed a plane mirror. So what will happen? These parallel rays, they will go towards the mirror, and because they are striking the mirror at 90 degree, so means they are perpendicular. So they will reflect following the same path. Means they will come back this way, and they will again meet at this cardboard sheet, and they will give you the image of that illuminated object on the screen. Let me show this to you. This thing. Okay, so what will happen? These rays which are going towards the mirror, this is your plane mirror, so this ray will reflect off the following the same path. It will come back this way. Okay, same way it will come back, because this is striking the mirror at 90 degree. You can see this, it is 90 degree angle. This one is also striking at 90 degree, so this will come back of following the same path. Now this also will come back. Now what will happen? After passing through the lens, they will meet here at this point. Okay, means the image of this triangle must have formed here inside the plane mirror. Okay, but we are not interested in this, but the rays, they reflect off. Okay, they reflect off and they meet at this point, and whatever the image was there, that will be seen here upside down on the plane, this cardboard sheet. You can see the triangle which is upside down. Okay, inverted image will be formed on this. If this happens, it's not blur, it's very sharp, well defined image. Means this distance, it is f of the lens. Okay, because the rays, you see the previous slide, this one, the rays which come parallel to the principal axis, after passing through the lens, they meet at the focal point. The rays from the focal point they will become parallel, right? So this is happening here in this also. So they whatever the image was, it will be formed on the screen inverted, and it has to be well defined. If you have adjusted is at the focal length of this, if this distance is equal to focal length, suppose this is 10 centimeter, if the lens has focal length of 10 centimeter, means this distance is also 10 centimeter. If the image is not clear, means the position of this thing is not right. Okay, so you have to move, you can move this forward and backward till this triangle, inverted triangle on the cardboard sheet is obtained. So you can move it forward, backward. Okay, or you can bring lens closer or away from it. Moving plane mirror won't do anything to it. Okay, either you move the lens, adjust the lens position, or you adjust the cardboard and filament lamps position object till you get the real inverted and well defined image. Okay, it shouldn't be blur. Because if well defined image is formed, you stop moving these things, either lens or whatever you were moving. Suppose you were moving this thing, so you stop moving it and measure the distance. So this distance will give you the focal length. Okay, how will you measure the distance? You will keep the ruler here. Okay, start from this position and this. Okay, so this distance has to be equal to the focal length of this. Okay, if it is not, the image is blur, means this object is not placed at the focal point of this, and rays are not becoming parallel. Rays will become parallel and reflect from the plane mirror in the same manner only when the object, that is illuminated object, is placed at the focal point of this convex lens. Okay, so for different lenses we have different focal length. Okay, some have 10, some have 20. Okay, depending on this thickness. Okay, thicker lens have shorter focal length and thinner lens has longer focal length. Okay, now other method, this one. Again we are making use of illuminated object. This is a cardboard sheet. We have made a hole in the cardboard sheet and we have placed a bulb or lamp behind it. So now the lens and this screen where you will get the image. Okay, so this method, you should know it, but the formula which is given here to calculate the focal length is not needed to be known. This formula, if it is a question, this will be given. Okay, so here the lens is placed at in the middle, not exactly in the middle, of course, depending on the focal length, but it has to be in between these two. Okay, the between the screen and the illuminated object. So here this is the question. The lens has a focal length of 15 centimeters. Suggest a suitable distance d between the illuminated object and the screen. It means from here till this, what should be the distance? Now you notice this is 15 centimeter. It means object has to be beyond the focal length so that the real and inverted image is formed on the screen. Okay, so it means we suppose this distance is 20 centimeter. Okay, object is placed beyond focal point of this. Okay, so if this is 20 and 20 on the other side. Okay, so and we know the case when object is between f and 2f, image forms beyond 2f. Okay, so if this is 15 and this is 15, 2f is 30 and this is 20, means 50 centimeter may be the appropriate answer. We have to count f is 15. Okay, so 15 plus 15, 30, and we have placed it at 20. So 20 plus 30 is 50, so 50, 60 centimeter will be the right answer. Okay, now the values are given. U is object distance and V shows here image distance. If you know the object distance and image distance, how do you find out? Using a ruler. Okay, and you have to avoid parallax error. Okay, the eye level should be perpendicular to the reading which is to be taken. So you will place the ruler. Distance between lens and the screen will give you image distance. Distance between object and the lens will give you object distance. This is object distance and this is image distance. So you will measure this, and here some values are given. 5 centimeter U, and this is 29 0.7 centimeter. We'll have to make the change here. We can calculate it. This is a different lens. See that this is the main thing, because if the same lens is there and object is at 5 centimeter, means it is placed between optical center and focal length, image will not be real. It won't be obtained on this screen. So this is another lens whose focal length is different, maybe 3 centimeter or something like that. Okay, so you will find it out by using this. You will substitute here 5, 29.7 divided by 5 plus 29.7, solve it, whatever answer comes will give you the focal length of that lens. Okay, so in this case, of course this distance, object distance, is not 5, this is more than 15 centimeter. So whatever are the values, you can calculate the focal length using measuring this distance, using the ruler, placing between lens and the screen will give you image distance, placing between this and this will give you object distance. Again, one thing, they should be in one line. Okay, the object, the line joining object and screen should pass through the optical center of this. You have to keep it in line, otherwise image may not be very clear, and you will make some mistake in measurement of the distance, object and image distance, right? And here this is another part, include the unit and give your answer to a suitable number of significant figures. So this factor is very important here, significant figures here. So unit of the focal length, of course, is a length, so it will be centimeter. Object distance is in centimeter, image distance is also in centimeter, that will also be in centimeter. And how many significant figure you can have, because your data has 5, means 2 significant figures in object distance and 3 significant figures in image distance, means you can have best to have only one significant, 2 significant figures, because object has the least number of significant figures. So our the answer will also have 2 significant figures, but in CAIE they allow one more than this, means 3, 2 or 3, but writing 2 significant figures, answer into significant figure will be better here, but you can write up to 3 because we also has this 3. Okay, so small equal to the least significant number, or one more figure greater than that, means 2 plus 1 means 3. Now let us start solving some questions. These are the questions on light. First one, mm, here this is the question actually in your textbook. So I have written the page number and Charles Chu. This is 4B. Okay, there is a person who is standing in front of a plane mirror. Okay, and they are asking, the person doesn't need this full length mirror to have to see his full image. So here you have to draw 2 rays, and one ray is, wait a minute, yeah, first part, the top of the head, you have to draw one ray from the top of the head and enters the eye. So let's see, from the top of the head and enter the eye, it is striking the mirror and it has to obey laws of reflection. So it means it will reflect from the surface of the mirror and it will enter the eye of the person. This is the normal shown in green color, it is entering this eye of the person. Okay, one ray is drawn. What is the next part? From the feet and enters the eye. You have to draw another ray which goes from the feet and enter the eye of the person. So it means it will start from here, this way, strikes the mirror and reflects, obeying the laws of reflection and entering the eye of the person. This is the normal. Angle of incidence has to be equal to the angle of reflection. So this is what we have done. See, the person's full length is full height is 150 centimeter, and it is mentioned in the question that eyes are 10 centimeter below the head, top of the head. So this distance is 10 centimeter. So what is the total height is 150. So how much is the remaining height? 140. Okay, so now see the next part of the question. Show the path taken by the light which travels from, this is done. Find the minimum length of the mirror to see full image, right? So it means to see the feet, see, this is the ray which is reflecting, striking the mirror, going from the feet of the person and entering the eye. So if you elongate it, produce it backwards, shoes are, it means this is the bottom of the mirror. This will be the bottom of the mirror. Okay, if it is shorter than this, above this, the person will not be able to see his feet. Okay, so this part is the bottom of the mirror, and upper part, see, head striking this part of the mirror and going back, means this point. So if this is 10, because this is 10 centimeter, if this is 10 means this is 5 centimeter, and this whole height distance from the feet of the person till the eye is 140. So this is half of 140. Half of 140 is 70 centimeter, and this is 5, means the length of the mirror will be 75 centimeter to show the full image. You don't need this lower part to see the full image of this person. Okay, so the lower part till here, because the rays they are going this way, and this is of course not drawn to the scale. This is just sketch, and but you have to remember the laws of reflection should be obeyed. Angle of incidence should be equal to angle of reflection. Okay, the page is given, you have to copy the diagram and you have to do it in your, this is the image of the person. Okay, dotted lines show that is the virtual image, and rays are not actually going this way. This is also thin line, this is also a thin line. Let us now go to the next question. A shoe shop puts a mirror on the wall so that customers can look at their shoes. The length of the mirror is 50 centimeter. A customer has eye 150 centimeter above the ground. Okay, this person has, I mean, this person is taller than the previous one. Okay, so this is the mirror, and the height of the length of the mirror or is 50 centimeter. They are asking at what height it should be placed. Okay, at what height it should be placed so that person can see his shoes. The bottom of the mirror is at a height of h above the ground. What is the smallest value of h that allows the customer to see an image of his shoe in the mirror? Here this is remember it, the minimum height they are asking to calculate the smallest value of h. It means the ray should strike from the shoes, they should be striking this lower part of the mirror and they should be entering the eye of the person. Okay, so since this part is 150 centimeter, this is already sorry, not the lower part, they will be striking the upper part. Okay, uh, so this is 50, means this will be 25 centimeter. Okay, because 75 centimeter length is needed. Let me take this and put it on the paint. Okay, so this h is not drawn to scale, for these two lengths cannot be equal, so I will just move it a little so that, okay, how will the rays go from the an upper part of the person, obeying the laws of reflection, they will enter. Okay, so since my measurements are also rough, but this is the thing, the laws are to be obeyed, means this is the normal here, and if I produce this back, the person can see his shoes in the mirror. So it means upper part you have to see. So this is 50, means how much it will be, because this is 150, half of this is, this height is, how much this height may be, half of 150 is 75. So this is 50, means this will be 25. If I change the question, what will be the maximum height of the mirror, then instead of taking to the top of the mirror, the ray from the shoes of the person to the top of the mirror, you will take it to the bottom of the mirror. Okay, so that what should be the maximum height so that person can see his shoes. So it means mirror cannot be raised above that height, means what will be that height, we'll change this mirror position and it will be this way. Okay, to see the image. Okay, so for the maximum height you have to take the ray from this to this. from the shoes of the person to the lower part of the mirror. For the minimum height, you have to take the ray from the shoe of the person to the upper part of the mirror. Now let us solve next question. So here the answer is B. An object O of height 3 centimeter is placed 4 centimeter from the center of a diverging lens. Figure shows the object O, the diverging lens, that is concave lens, the two focal points f1 and f2 of the lens. Determine the focal length of this lens. What will you do in order to determine the focal length? You will measure it. See, the 5 small squares are 1 centimeter. So you will start measuring from f2 to this or f1 to the optical center. Count how many are there. 1, 2, 3, 4, 5, 6 centimeter is the focal length of this lens. You check it, you confirm it, verified by measuring the other side as well. So you will get the focal length. So just drawn to scale. So you measure that and write the answer, that is 6 centimeters. Sometimes they write the scale, the diagram is 3 times the scale shown. So it means if it is 3 times the scale shown means 6 3 is 18 centimeter, right? So this is how you can get the right value of the focal length. Determine the focal length. We have determined. The diverging lens produces an image of object O on figure by drawing rays from the tip of O. Locate this image and label it I. So what will you do for this purpose? This is the diagram. Here I have to take the ray starting from top of the object. Okay, so this thing I will take it to this, and till the central line here. Now will the ray go through this? What will I do? It's not converging lens, diverging lens, so ray will not go to this f2. Okay, so instead it will be appearing as if it is coming from f1. So what will I do? I will start from here, f, and this has to be very dim because it's not the real ray. Then I will take this ray forward, okay, in the same line. So this is the ray going. So this is produced there. Now still we don't have the position of the image. Now other ray, what will be the second ray? I will take it from the, because one ray is not sufficient to draw, to locate the image. We need at least 2 rays. So I have to take another ray. So what will I do? I know that a ray coming towards the optical center of the lens will go undeviated. Okay, so I will draw this. So this ray is going undeviated, passing through O. This is your O. Now the point where these 2 rays are striking, okay, the image is formed. Since this ray is not real, okay, this one is real, but this one is not real. It means image will be appearing at this point, and it will be virtual image. Sorry. Upright, because the rays are coming from the top of the object. So this will, and they are where they are striking, that is also showing the top of the object. So this is your eye. So image distance, you can measure this distance from the central line till this. And let's see what is the other part of the question. determine the focal length. We measured it and found it out, and we also drew the two rays and we located the image. Determine the height of the image and determine the magnification. So height, what will you do in order to measure the height of the image? This height is to be measured. Okay, so you count this. It is five blocks are one, two, three, four, five. One, two, three, four, five. Five blocks are equal to 1 centimeter. So 1.2, 1.4, 1.6. It means 1.6 or 1.7 centimeter is the height of this. Okay, 0.1 centimeter error may be allowed. Okay, half of the small square. Okay, not more than that. Okay, now this is the height of the image. And what is the height of object? Height of object is 1, 5 blocks, and this is 2, and this is 3. So magnification is what? M is equal to I, image height, divided by object height. So you will write that 1.6, and here you will write 3. So this answer will give you magnification. Magnification tells us how much bigger image is with respect to object. So here this is because the numerator is smaller, it means image is smaller. Okay. Now let us do another question. This is related to convex lens. Now here the converging lens has a focal length of 3 centimeter. It's not marked here, so you will have to, I think, mark the 5 blocks again. In this are 1 centimeter. An object of height 2 centimeter is placed 5 centimeter from this. You can confirm also from the center 1, 2, 3, 4, and 5 centimeter from the center of the lens. Figure shows the arrangement of the object. On figure, draw rays from the top of the object to show how the lens forms the image, and mark image clearly. The image is magnified. State one feature of another feature of the image. It will be real. Okay. Calculate the linear magnification. In this, what we will do? We will draw two rays, one from the top of the object going parallel to the principal axis. Okay, and from here it goes through F. F you will have to mark. What was written in the question? Mm, 5 centimeter. Okay, sorry, 3 centimeter. So 3 centimeter means where the focal length is. I have to locate 5 blocks, 1, 2, 3, 4, 5, 1 centimeter. 1, 2, 3, 4, 5, 2 centimeter. 1, 2, 3, 4, 5, 3 centimeter. Okay, so this is F. It means my ray will go this way. Okay, and of course, two rays are needed. Arrow, put an arrow to show this is the ray going this way. Now, another ray, we can do that one, common one, going striking the optical center. Okay, this is the point where the rays are meeting. That will be the position where image is formed. It means the image is formed here at this point, and I have to elongate a little. so that my intersection point is clear. So here I will have real and inverted image. If I'm not mistaken, okay, then you will put two arrows to show the direction. This is image marked clearly. This is I. And what is the size? Object is having height of 2 centimeter. What about the image? 1, 2, 5 blocks 1 centimeter. 1, 2, 3, 4, 5. 3 centimeter is the height of the object. And object distance, what we will do to measure the object distance? Of course, we will measure distance from here, from the center of the lens till this position. Okay, you will count the square, you will get the image distance. Right, of course, it is more than 5. This is 3, so it will be most probably 3, then 4, 5, 6, 7, 7 point something, 7.6, because one small square is 0.2 centimeters. 7.6 centimeter is the image distance, and height of the image is 3 centimeter. For the magnification, image height over object height means 3. For magnification, it will be 3 over 2, means 1.5 times it is bigger than the object. Okay, so we have solved all the parts of this question. We linear magnification, linear. There is angular magnification also, but that is not in your syllabus. Linear magnification simply is the ratio of image height to the object height, or image distance divided by object distance. Now, sometimes uh, image lens position is not given. Object and image position is given. So, what do we do? How do we locate the lens? So, in order to do that, let's have a look at this. Object and image. We know that ray coming from the top of the object, it will pass through the optical center. So we know the point where ray will be starting and the point where the ray is going to end. Okay, so from the top till the top of this. So that's how we got the position of the lens. Now what we will do, we can draw a lens here at this position. Draw a vertical line, the point where the ray is striking, passing through principal axis. Okay, so this is the position of the lens, and you may label it L. Okay, and try to draw it bigger than the object, so that you can easily draw rest of the rays. Now how will you get the position of the focal point? Now, because we know this point, so we can obtain the position of the focal point easily. How will you get the position of the focal point? Draw ray this way, ray parallel to the principal axis, and we know this point also. So take it to this. Now we have located F also. So where is F? This. Measure this. Okay, distance using ruler, and mark same F on the other side at the same distance. So suppose if this is 5 centimeter, means F will be 5 centimeter on the other side also. So that's all for today, and do these questions again in your answer book and give me the feedback. Allah Hafiz.